I'm Christian. I'm with Bitmovin for almost a year now, working from Berlin, where we have our coding team, codec development team. So we're working now in codecs, in the actual encoding and decoding engines. And before that, I was with the University of Aachen. Maybe some of you know Jens Rainer Ohm. He was my professor at the university, one of the chairs of JCTVC, of the MPEG standardization stuff. And basically, scalable video coding was also one of the topics that I've been working on in my PhD thesis I did there. And a lot more in depth than this. So it's built on top of scalable video coding. So basically, the reduction of complexity in scalable video coding, that was my topic there. Yeah, very scientific stuff, as always, as a PhD thesis is, right? Really specialized stuff. Today, I want to give you a small introduction about scalable video coding. I was really unsure how technical the audience would be, but I guess all of you have to do with video coding. That's cool. I don't know how many have had any experience with scalable video coding or know what it is, have been working with it. Okay. So that's cool. I wanna introduce, but that means that there are some people who I can actually maybe teach something, I hope, or show something. I wanna go a little bit into the details of video coding, of scalable video coding. It has been around for a long time. Usually people, when you're talking about scalable video coding, are thinking about SVC, scalable video coding, the scalable extension of H.264 AVC, but there are a lot of other standards which also support scalability features. So reaching back to MPEG 2, where also some features are in, and of course also the most recent standards, HEVC, AV1, VP9, also have scalability features in there. They all work similarly, but also have a little bit of different approaches to the same thing. With different trade-offs between complexity and coding performance. And I want to show a little bit what the concepts are, how they are implemented, and how they are used in the end. And then, of course, scalable video coding has always been a little bit of a scientific topic. There have been some deployments of it, but I mean, we all know it hasn't been adopted widespread in that sense so far. And I want to go a little bit into the details on why, what the main problems are, and how this could be improved. Okay, I want to start at the very beginning. So scalable video coding, what is it? Basically, the idea is that in scalable video coding, you have multiple videos of the same, so multiple versions of the same video in one bit stream. Usually you refer to it as layers, so you have multiple layers, and the layers differ in, there's multiple things that they can differ in. Like you can have an additional layer which increases the frame rate. You can have an additional layer which has the same video just at a higher spatial resolution or at a higher quality. So those are usually those are the three things you can scale in the bit stream, and it's all embedded into one bit stream. And the idea is that you use dependencies between the layers in order to compress it more efficiently than having independent videos. That's the whole idea of it. And then you can add multiple features of adaptation and flexible adaptation to it and things like that. There's multiple applications where this is really useful. For example, you can adapt to different device capabilities. You could adapt, also if you're thinking about adaptive streaming, you can adapt the bitrate basically, so for the same resolution, or you can change the resolution also a little bit if you're thinking about per title stuff. You can adapt to changing bitrates in streaming applications. And of course, in the end, it also has applications where you want to reduce the storage or the transmission cost when you're transmitting multiple versions of the same video. That's the idea. You are exploiting the dependencies between the different versions. That's always the underlying concept. And I wanna get into this from the bitstream perspective a little bit. This is an example for HEVC, but of course for all major other codecs, it's basically the same. Everything within a bitstream is packed into packets. into units, basically. For HEVC, these are called null units. In other standards, they are called, for example, in AV1, they are called OBUs, Open Bitstream Units, but it's basically everything is packed into units, into small packets. In this example, Bitstream, we have a few parameter sets at the beginning. So the first 3 units are the video parameter set, sequence parameter set, picture parameter set. Those give basic information about the video. What's the resolution? What's the frame rate? There's a bunch of information in there, but no actual coded frames yet. And then, of course, we start with the frames. So there's frame 0 first. Then the next one is frame 4, frame 2, frame 1, frame 3. You can already see that the order they are coded in is not the order that they are displayed in. That's basically also have been around since MPEG 2. It has some advantages. I'm going to come to that later. Of course, the first frame, there's some letters below there. The first frame is coded as an iframe, so basically as an intra frame. You don't have any reference frames yet. You don't have any information about the sequence yet, so you have to encode it self-contained. So the iframe can be decoded self-contained. It doesn't have any dependencies on anything else. You can always decode it. The next frame, frame 4, is a P frame. It uses prediction, pre-P. So it uses the information from frame 0. Usually, motion compensation, right? So you all know that concept, I guess. You use the information from frame 0 you already have to do a good prediction in frame 4. So you copy information over. Basically, it's like a puzzle. You take out a piece, move it a little bit, and put it into the new picture, and usually it's a good prediction for the current picture, because usually in video sequences just something moves. Usually you don't have rapidly changing pictures. You usually have movement in there, and that movement you can, in most cases, very well map with motion compensation. So just moving blocks around, copying them. And then, of course, frame 2 is a B frame, which means this one predicts from 2 sides. It can use frame 0 and frame 4. So basically, it can look into the past and into the future. And that, of course, makes it even more efficient to predict. If you know how the frame used to look, and if you know how it will look in 2 frames, you can do a much better prediction of it. And this is the basic concept of a unit. How does scalability come in there now? Well, basically, from the Bitstream side, it's quite easy. We want to have multiple versions of it, or multiple different renditions, and we can take a look into the standard. This is just this is from HEVC, but as I said, in the other standards it looks similar. This is the null unit header, so each unit has a header, and in the header there's the null unit type is indicated. Is it a frame? Is it a parameter set? There's a layer ID and there's a temporal ID, and those are the ones which indicate the scalability stuff. So we have a bunch of layers, and in the first 2 bytes of the header we can already identify what layer the unit does belong to. And that gives you a lot of advantages. It works in other codecs as well. That gives you a lot of advantages when you're thinking about easy parsing or decoding or discarding of bitstreams. So you have a scalable bitstream and it has multiple layers. You can just go through it unit by unit and say, okay, this one belongs to layer 0. We need it. This one belongs to layer 1. Let's just kick it out. And then you will get if you do that, you will get a compatible bitstream out of that. So it's a very easy way to discard stuff from the bitstream. That's from the bitstream side. And next, I want to go into the whole prediction stuff. How does the stuff actually work under the hood? I want to go from the hierarchical prediction stuff. So some of you might already have seen this or know how this works. Usually, for video coding, in this example, we will encode 5 frames. We have to start somewhere, so we encode frame 0 first. It's an intra frame. It can always be decoded self-contained. It doesn't depend on any other frame. Then we encode frame 4, which is 4 frames into the future. And of course, we use the information that we already have. We already have decoded frame 0 or encoded frame 0, so we can use that as a reference. So here we have this arrow, and basically this arrow means we use the information from frame 0. Usually motion compensation. So you use the reconstructed image as a reference image, and you can just copy information over, do a good prediction, and just encode the error signal. And that gives you a lot of advantages. So bitrate-wise, frame 0 is really big, frame 4 is much, much smaller because you have this reference. Then we encode the frame in between, as I said, the by-predicted frame, right? So we can now use information from frame 0 and 4, so from the temporal past and future, which gives us an even better prediction because we know how it used to look, how it will look, so we can combine this information to do an even better prediction, right? If you know how it used to look, how it will look, you can see, okay, there's something moving from here to here, so probably in the middle it's somewhere in between. And then you can do a much better prediction. You get even lower bitrate for this picture. And then, of course, the last hierarchy is the frames in between. Even closer temporal prediction using both directions, so much, much smaller, right? So, and this is a typical hierarchical prediction structure that you apply. This has been around from, MPEG-2 started with it with a very small hierarchy. AVC has it with a bigger hierarchy. In HEVC, you can have tons of pictures having a giant hierarchy, and basically in AV1 it's the same. You can have hierarchies spanning a lot of pictures, doing this by prediction into all directions. Okay, so far this is not scalable. This is just one video. And now what do we do to do this scalable? As I said, the streams can differ in various things. One of them is temporal scalability. So you can have a higher layer which has a higher frame rate than the lower layer, and basically we can generate this from the non-scalable bitstream quite easily. So first, okay, we have to define some layers. This is layer 0, layer 1, so we have 2 layers here, and what we can do now is basically define every second picture as belonging to the higher layer. So we just move them up there. And yeah, this is it. We have temporal scalability because we can decode all pictures from the lower layer, right? They only depend on each other. And we can discard picture 1 and 3, no problem. Then we have half of the frame rate, or we have a certain frame rate. And if we add the units from the higher layer, we get twice as many frames. So we have a hierarchical stream, right? We can just kick out frame 1 and 3, and we have a conforming stream which you can decode, which has half of the frame rate. And that's it. That's temporal scalability. Of course, this is a factor of 2. You can also think about prediction structures where you have different ratios. It doesn't have to be 1 to 2. You could also add 1 additional frame every 2 pictures, or every 3 pictures, or every 4 pictures. So there's a lot of options you can do here. But this is the basic concept. Pretty easy, pretty straightforward. And now we're going to come to the actual other stuff, to spatial and quality scalability. So in spatial or quality scalability, you have multiple versions, or in our example, we will always just think about 2 layers. Of course, there can be more than 2, but just so that you can still see something in these graphs. So we'll only consider 2. Spatial and quality scalability are here delta as 1, because in principle it's the same concept. In spatial scalability, the spatial resolution of the image increases. In quality scalability, the resolution is the same and just the quality increases. And basically, it's the same concept, right? In one of them, you need an upsampling filter. In the other, you don't, or you have an upsampling filter of 1. I mean, and concept-wise, they are the same. They are basically the same. So what do we do now? Okay, still we define 2 layers, right? We want the layer 0 bit stream as before, which we can decode, but we also want another version of the same video at a higher quality or a higher resolution. So we basically have to encode another picture at a higher quality in the higher layer. We could do this as another iframe, self-contained. But of course, that's a bad idea because we already have the information from the lower layer. And a self-contained frame is always bitrate-wise very big. So why not use the information that we already have? And that's the idea of scalable coding. Instead of having independent videos, you use the information that you already have from the lower layer. So we draw this little arrow and use the lower layer picture as another reference. So you can apply the same concept as motion compensation just from the lower layer, copy the picture up, and just refine it, or just add information, just encode the error to the original. That's one of the basic ideas of it. And now we can go on. Of course, we don't only want to code one frame, we want to have more. We can go on, we encode frame 4, and instead of only using the frame 0, we also use the information that we have from the lower layer. And the same goes for the other frames. For frame 2, we use 0 and 4 from the higher layer, but also the information from below, and for the last pictures, of course, as well. And that's the whole thing of scalable coding. So this is one of the basic concepts of it. You use the information from the lower layer to do a better prediction and lower the bitrate, of course. And yeah, we can already see some things here. So the cool thing about it is, okay, what happens now if the higher layer is missing? So if all of the higher layer pictures are missing, no problem. We can still decode the lower layer pictures, right? There's no issue there. Of course, if the lower layer is missing, we can't do anything because we need the pictures. And we can already see that this concept is a little complex at the decoder side, because if we want to decode the higher layer, we also have to decode the lower layer. We have to. We need the reference. We need the image. There's nothing. We have to do the reconstruction of all pictures if we want to have the reconstruction of the higher layer. And that's basically it. But yeah, and this is one of the schemes to do it. So the question was, what is, I mean, in layer 0, for example, we're using motion compensation, so we're using the reconstructed pixel information to do. So the arrows basically mean that. But what do the arrows mean between the layers? What is going up between the layers? It can be various different things. Of course, it can be the reconstructed image itself. So like motion prediction, you can just have another reference frame, which is the lower layer reference frame. Of course, if the resolution changes, you have to perform upsampling. If just the quality increases, you don't. But it can also be motion information from the lower layer, which could help in the higher layer if you already know how something moves. Or it could be prediction information, which prediction modes are used, for example, which intra-prediction mode is used or something. So there's multiple things that can go up here. That depends on the standard that you're using. For example, in SHVC, it's pixel information and motion information. In AVC, it's only, or in SVC, it's only, it's not pixel information, it's only motion and residual information and intra information. It depends on the codec, what goes up there. And then in the higher layer, you're doing motion compensation again. That brings me to the next topic, which is basically loop control. That's also how you code. Where is the loop controlled? Because the scheme I just showed isn't the only one you can use. You can also think about other schemes to connect the arrows to each other, to use the references. There's advantages to it, disadvantages. It depends on the application, as always, and there have been different standards using different versions of this. First of all, I want to show a simple one, which is actually not used in any video coding standard because it doesn't make a lot of sense, which is basically in the lower layer, we're using the normal prediction structure between the pictures, but in the higher layer, we're not using any interprediction between the pictures. So we're just using the information from the lower layer. The advantage here is, of course, if just one packet from the higher layer is lost, like packet, I don't know, for picture 0 in the higher layer, we can still decode all of the other frames in the higher layer. So that's good. On the downside, and of course, we need a little bit less of decoder complexity because we don't have to perform this interlayer prediction in the higher layer. That's also good. But the coding performance of this is really bad because the interprediction in the higher layer actually gives you a lot of coding gain. And yeah, if you get rid of this, then your coding performance just drops down. So this has actually never been, there is some schemes where you can, there is some standards where you can use this, but I think never, I think nobody ever really used this in reality. But what I want to do here is transition somehow to the pure opposite of this. So this is control in the lower layer. We only have one loop running, which is in the lower layer. And the opposite is, of course, loop control in layer 1, so in the higher layer. And I'm going to go through this picture by picture because the resulting picture is going to have a lot of errors. And if we build it picture by picture, I think you can understand it better. We're going to start, of course, coding order. We're going to start with the first frames of layer 0 again, intra-frame, self-contained, okay. Now we're going to code the higher layer picture, which we code using the information from the lower layer picture as before. And now it's getting interesting. Now we're coding frame 4 of layer 0 again, right? That's our coding hierarchy that we're using. But why not use the information from the higher layer picture 0? Because it has much better reconstruction quality. It has more information. It gives you more compression performance in the end. Why not use that, right? And this is the idea. So we're now using the reconstruction from the higher layer for picture 4, and now it goes on like this. So now we're coding picture 4 of the higher layer, which uses, of course, the lower layer one and the frame 0 of higher quality. Then picture 2, and instead of using the references from the lower layer, we're using the one from the higher layer. And this is how it goes on. So picture 2 in the higher layer, we're using the higher layer references and the lower one. And then for the remaining 2 frames there, we're also using the higher layer references. And then, of course, for the frames in the higher layer, we're using the ones from the lower layer. One of the advantages of this is that you have a higher overall compression performance. The compression performance of this is really good if you're decoding the higher layer. But of course, if you want to decode the lower layer, then you will run into some problems. So what happens, this is what I'm going to now drift, right? So what if the higher layer packets are not available? We want to have a scalable bitstream, as I said, so we want to be able to kick out all of the packets from the higher layer to get one version at the lower resolution or quality. And what if the higher layer packets are not available? Well, then our errors are somehow pointing into nothing because the pictures are not available. We don't have the information. We can't reconstruct this. What do we do now? Well, we can just replace the references by the references that we have from the lower layer, right? We still have a reconstruction of picture 0, just not at the higher quality. We also have a reconstruction of, then we can reconstruct picture 4, just not at the higher quality. And then it goes on like this, and basically you replace all of your references, and what you get is you get a reconstruction, but of course it will have errors because it's not the original references that you used, and so all of the pictures following will have errors. And this is also called a drift, because the encoder assumed you're using different references, but the decoder doesn't have them. So encoder and decoder drift apart. And yeah, you can see that in the PSNR results. If you look at it and remove the higher layer bitstream, you can see that the quality just, over time, just goes down to horrible, horrible values. But just to say, this is the sheer opposite of the layer 0 control. This is complete layer 1 control. You're always taking the highest possible quality as a prediction. And yeah, that's the... But you're right. You cannot reconstruct it drift-free. That's true. So this is loop 1 control, basically higher layer control. And the last thing I wanna go into is basically a hybrid scheme, because you can also do something between these two extremes. Use the higher layer references, but not for all frames. And usually this is also referred to as the key picture concept, and basically you define periodic key pictures. We will define picture 0 and 4 as key pictures, so every 4th picture is a key picture. You can also do bigger difference. In reality, it's more like, it depends on the configuration, but you can have like 4, 8, 16, or that's 12, usually a larger distance between the key pictures. Also, it can also depend on the content that you're encoding and things like that. So we're defining picture 0 and 4 as key pictures, and for key pictures, the rule is key pictures in the lower layer can only predict from other key pictures in the lower layer. They do not predict from the higher layer. And that gives us a big advantage because we can always reconstruct these pictures without errors. And that's the big advantage here. The pictures 1, 2, and 3 in the lower layer still use the higher layer references, but pictures 0, 4, and then of course 8 and the following, every 4th picture will not. And also we imply another rule which says that the that the prediction breaks at every fourth picture, so that the error within the structure does not propagate to the next one. And then we have the same problem, right? What if the higher layer is not there because we discarded it, or we don't want to decode it, or we got rid of it? What do we do now? Well, we still have some arrows pointing into nothing because the references are missing, but we can do the same as before. We can use the pictures that we have from the lower layer, reconstruct picture 1, 2, and 3 in the base layer. Of course, these will have errors. 1, 2, and 3 will have some drift. They will not be the original, but now the drift is contained within these frames. Picture 0 and 4 are drift-free. Pictures 1, 2, 3 have drift. And then the following pictures, 5, 6, 7 will have drift again. Picture 8 will be drift-free. And so you have a drift within the hierarchy, but it's contained. It's never escalating to infinity. And that's one of the basic concepts. So this is the hybrid or key picture concept, or the hybrid loop control, basically. And this is a compromise between the two, but it has a lot of advantages. It gives a high coding efficiency. It gives you the flexibility of having multiple layers. You can actually discard packets in the higher layer by random, and you can still reconstruct something. You have drift, but it's contained, and you can control the drift. That's the advantage of this. I just wanted to show a picture. This is some experiments I did showing the drift. So basically up there we have the higher layer. You can see the hierarchical distance is a little longer here. It's actually 8 frames. That's why every 8th frame has a higher reconstruction quality, and then there's the frames in between, and then every 8th one has a higher reconstruction quality. And the yellow line is basically the lower layer. So we discarded the higher layer. We are just using the lower layer. And the yellow line is the reconstruction without drift, using a drift-free hierarchy. And the turquoise line below that is the one with drift. You can see that all pictures between the two key pictures, here every 8th picture is a key picture, have some drift. The reconstruction quality is lower, but the drift is constrained. It's not accumulating over time. It's not ruining the whole thing. And that's what happens then in practice. And now I want to we saw a lot about the concepts and how the whole prediction thing works, and now I want to show a little bit of which of the coding standards which are out there actually uses what. And as I said, one of the first codecs to have some scalable features is MPEG-2. Then there's AVC, H.264. The scalable extension was called SVC. Then there's HEVC, which has a scalable extension named SHVC, and then there's AV1 and VP9. I put them together because technically they are very much the same from the scalability standpoint, of course. Everything else changed a lot, but from the scalability standpoint, they are very, very alike. So let's start with MPEG-2. MPEG-2 does not support temporal scalability, just quality and spatial scalability, just in some specific configurations. And MPEG-2 actually uses layer 1 control, layer 1 loop control. And as I said, or as we saw, that's a bad idea for the reconstruction quality of the lower layer. And this is basically what you can see in MPEG-2. It's the decoder complexity is quite low, but the drift is really high, and you can simply implement it, but in the end, you don't really want to decode the lower layer by itself, because that will not look good. So it was a first implementation of a scalable scheme. I think this has never been used. It was basically the main point, or the main focus for the standardization by then, was the decoder complexity, because with the higher layer loop control, you only have to decode the higher layer pictures. You don't have to decode the lower layer pictures, and that gives you a giant advantage at the decoder side. Basically, they said, we cannot add any complexity to the decoder. It's complex enough. This doesn't work, and that's why they chose this scheme. You have to consider it's 1995, the days of Scatman's world. So there wasn't a lot of computing power back then. So this was a very crude compromise that they did. Then there was AVC, or SVC, which is actually a really cool scalable coding scheme. It supports all types of scalability, and it uses this hybrid loop control that I showed. So the key picture concept, basically. That's what they implemented. And they basically combined all of this, and in the end, they got a scheme which has a very low decoder complexity because you don't have to decode all of the frames. So the decoder complexity doesn't increase that much. There is drift, but it can be limited and controlled very well. But of course, one of the disadvantages is that the implementational wise, it's quite complex. If you want to implement this in a decoder, then you need some good engineers to do that. Also in the standard, it looks really confusing. It's not that easy to do because it comes from an academic idea basically, and it wasn't wasn't that good to use in the end. But it is highly flexible. You can combine all of the different types of scalability. It has a high performance, and it has actually been used in some applications. Mostly conferencing applications, but I think most companies don't want to see what they're using under the hood, but I've heard that some are using actually SVC, also officially. I think, didn't Google Meet once use SVC before they switched to VP8, I think there was something. So this was the one which has actually been used so far. Then after the standardization of HEVC, there was an activity to do scalability with HEVC. So as HVC was standardized, that was the one standard that I also worked in. I've been to a lot of meetings there. Also supports all types of scalability, also all combinations, but it uses a multi-loop approach. So if you want to decode a higher layer, you have to decode all layers. You always have to decode all layers, and that adds a lot of complexity at the decoder side. Of course, with that approach, you also have no drift, and the implementation is rather simple. You basically only, actually HEVC or SHVC has been standardized in a way that you can simply put another decoder on top, say, these are the references from the lower layer, and it works. There's really just very little you have to add there, which was very attractive for the hardware manufacturers and software manufacturers. You just could, the hardware manufacturers loved this because basically they said, hey, cool, we can implement a decoder by just putting 2 chips on there and wiring some stuff, and that's it. Basically, the higher chip just needs access to the reference picture buffer of the lower one, that's it. That's the approach they chose. I proposed something different, but it wasn't chosen in the end, unfortunately. which also brings me back to my PhD thesis, which is basically on an SHVC version at a much lower complexity at the decoder side. That was the main idea of my thesis. Unfortunately, they went with the other approach. Yeah, let's see. AV1 and VP9 also have scalability schemes supporting all types. And the cool part about that is that AV1 and VP9 actually already support mostly all tools to do this. They have a concept of encoding frames which are not displayed, like the lower layer if you're decoding the higher one. They have a concept of scaled reference pictures. So if you're thinking about spatial scalability, all of the filters are already in there. You don't have to add anything. And so it was really easy to add that in both of the standards, and that's also what they did. You also have a multi-loop approach, so the decoder complexity is high, but you don't have drift. The implementation is really simple because everything is there. But on the downside, they chose a scheme where actually the number of configurations is really limited. So there's a set of configurations you can use, and you have to choose of one of them, and basically there's like, I don't know how many, 16 or something. So one says you can use 2 spatial layers and 2 temporal layers. One says you can use, it's just a set of 16 different configurations you can use, and that's it. It's not that flexible as the other ones. And now I want to come to the last point, which is basically what SVC or what scalable video coding is good at, but also why it's not that used. This is a simple coding evaluation graph. I think most of you know what this is. There's the bitrate on the x-axis, the reconstruction quality in PSNR on the y-axis, and we have 3 graphs here. The leftmost is HEVC, single layer, Nothing special about that. 4 rate points. That's the performance of HEVC. On the very right, there's HEVC simulcast, which basically means we have 2 different versions of the same video, one at a high quality, one at a lower quality, and we're transmitting both. So the bit rate is higher, but the reconstruction quality is the same. So we're just adding another, this is basically, simulcasting 2 different streams, right? So we increase the bit rate, but we have the option to switch to the lower reconstruction quality. But there's no information between the layers is used. And if you're thinking about scenarios like that, actually SHVC can save you a lot. The yellow line in between, that's SHVC. You can see it's much closer to single layer coding than the right one with the same qualities, right? So for the SHVC one here, you can reconstruct 2 versions of the same video at a higher and lower quality, 2 different bit rates. But as you can see, you can save a lot of bit rate for this compared to just transmitting 2 videos independently of each other. Of course, it's a good question what the application of that is, transmitting 2 videos of each other, independently of each other. But there's actually, there's some scenarios where this is done. But as I said, this shows what SHVC is good at. You can see, compared to these simulcast scenarios, you can save a lot of bitrate. But on the other hand, you can see that compared to single layer coding, to just transmitting 1 video, you also lose something, right? There's an overhead. It moves a little bit to the right. There's a bitrate overhead. And that's typically, what kills scalable coding, because the overhead is usually low, but this is a scenario with 2 layers. The more layers you have, the worse it gets. That's just the basic problem. If you're thinking about a scenario with adaptive streaming, where you have 10 layers of the same video, the overhead will just get too big. And that's one of the main problems. But it might be an application for just a few layers. When you're thinking just about the highest layers, you could actually do something, some really cool adaptation things. Because as I showed, there's schemes where you can actually, where you don't have to choose to just decode one of the versions, but you can actually discard just some packages from the higher layer. And so you can more flexibly adapt the bitrate. In classical streaming, you have multiple versions of the same video, and basically you try to transmit the best one you can, but in the end, the problem is always when you're missing 1 packet from the highest version, because the bitrate is just not there, you cannot decode it, and you have to switch to a lower resolution. And in scalable coding, there's some tools where you can actually decode something which is of much higher quality when you just lose 1 packet. It's not that bad. You can switch to the lower one. You can actually have smooth adaptation to the quality, and that's one of the really cool features about it. Probably there has to be more research on this, or it has to be seen how you can actually put this into applications, usefully into applications. But I think there's some potential here to have even more adaptive streaming in the end. That's a very good question. I'm actually not that active in Dash. I don't know if they are talking about stuff like that. Because the problem is, Dash usually, you do adaptation on a video stream basis. You just have multiple streams and segments, and you download them or not. If you're thinking about scalable coding, you have to break everything down even further. You can actually break down a video stream into each layer, each frame. And then you don't have a segment of 4 seconds, or in a segment of 4 seconds, you would have 4 times 24 frames times 2 layers or 3 layers, and then everything gets even more complicated. But in theory, you could do that. You would have even smaller blocks, and could also do an adaptation using like HTTP GET, just download not segments, but single packets, or just a set of packets, and then see what comes in. And then you could do the most important ones first, the lower layer first, and then when you still have bitrate left, you're done. Then you do the higher ones, and then add information on top. That's one of the additional features of SVC. So in SVC, you're actually not using the reconstructed pixels from the lower layers, but you're just using the information from the bitstream from the lower layer. You're just using motion information, the transform information, the residual information, and the, I mean, everything that's in the bitstream, but you're not decoding anything. And the cool thing is that you can actually, flatten multiple layers in a certain configuration in SVC. You can flatten multiple layers using a simple bitstream rewrite. You don't have to actually decode something. You can just rewrite everything, and then you have a single layer bitstream for the higher one. But again, it's cool from an academic standpoint. There might be some applications where you want to use this. I think this has never been used because you always have to consider, in that scenario, you always have this this overhead, right? The scalability overhead of like 10 to 15% or 20% depending on your configuration. That always comes on top, and that's what you lose in the final bitstream. So most often it's just more efficient to re-encode just using AVC. In theory, you have basically a bigger, if you're scaling it up and use that as a prediction, you have a bigger block, which you predicted. But of course, the resolution of the lower block is also lower. So, I mean, by the upscaling, you don't add information to it. You have a low-pass filtered bigger block, basically. And that's one of the problems. You're losing a lot of information there by it's just lost in the lower quality or in the lower resolution. And that's why you still get a loss there. If you had a bigger block using a higher quality reconstruction, you would probably gain something, but the source is just subsampled and has less information, unfortunately. And I'm not aware of any device actually supporting it. Of course, it's all hidden in the profile and everything, but and I said that you don't have to add anything on top, which is not entirely true, because the decoder, of course, if you have multiple layers and you're actually doing the decoding in a multi-layer scenario like you're doing here, the decoder, of course, has to be faster because it has to decode more frames. And then you have to actually do something in the hardware. You have to make it run faster or add more units or whatever to actually make it work. And probably the hardware is more tuned for a specific level, like 1080p at 24 frames. And then if you want scalability, you need more power, and that's probably not been implemented. That's a really good question. I also think there are a lot. I mean, the current scheme, which is widely used, is more the dash approach, right? You just have segments of different versions. You just download them. If it doesn't work, you download another one. In the background, you download a backup resolution at lower resolution, just transmit another one just to have in case of backup. It's the easier approach, probably a little bit. And of course, you have the overhead of scalable coding. But of course, then when we're thinking about adaptive bitrate streaming, you also transmit a lot of information you don't decode in the end. So there's also an overhead there. And yeah, it's a really good question. Me, I'm an engineer. I've been working on this for quite a while, and yeah, I did a PhD thesis on this. And I think there's a lot of potential to actually deploy this in practical applications. Thank you.